Hello everyone, my name is Naval Santos and I'm a PhD student at London Metropolitan University under Professor Balvedi and Dr. Sharam. Today I will be talking about my project research and the title of the project is Selective Prioritization of Real-Time IP Packets to Improve Quality of Service in 5G Wireless Sensor Networks. So the main focus of the project is to investigate, review and evaluate quality of service problems, more precisely end-to-end delay and reliability for ultra-reliable low-latency communications, and also develop a novel scheme to improve quality of service for 5G wireless sensor networks using artificial intelligence techniques. The 3GPP specifications defines three major scenarios for 5G networks, and these are enhanced mobile broadband, massive machine-type communications, and ultra-reliable and low-latency communications. Uh, for quality of service support in 5G networks, we have three major technologies, which are software-defined networks, network function virtualization, and edge computing. So before proceeding, I think it's important to define quality of service in the context of communication networks. So quality of service for communication networks refers to reliable and timely data delivery with performance metrics such as packet loss, latency, throughput, reliability, and energy efficiency. So, to tackle challenges facing data delivery in wireless sensor networks, artificial intelligence techniques are being widely used, and this is because they offer great potential to address the problems facing ultra reliable low latency communications and related applications. Examples of these applications are factory automation, remote surgery, and self-driving cars. With regards to the motivation for this project, 5G networks or 5G wireless sensor networks still facing challenges in delivering high quality services while meeting the demands of ultra reliable low latency communications. And one of the main problems is latency. So 5G networks employs technologies such as edge computing to minimize latency. However, achieving ultra-reliable low latency in the sub-milliseconds range is still very challenging in certain scenarios. Another problem is reliability. So 5G network employs techniques such as redundant transmission and multi-connectivity, for example, to improve reliability. Nevertheless, it's still very difficult to achieve extremely high reliability for ultra-reliable low-latency communications and associated applications. So it may require additional measures and optimization procedures. Overall, the randomness nature of wireless networks, for example, environmental factors, device capability, and the complexity of ultra-reliable low-latency requirements even in wired network scenarios, still posing great challenges to consistently meeting the demands of ultra-reliable low-latency communications in all scenarios. Therefore, a great deal of research is being carried out, and the development efforts are focusing on optimizing 5G networks, refining protocols, improving network deployment, and developing specialized techniques to better address ultra reliable low latency communications specific requirements. In terms of background of the research, initial work to enable ultra-reliable low-latency communications was included in the specifications of 3GPP releases in 2016, And the IEEE developed a standard, which is the time-sensitive networking, aimed at addressing the problems facing ultra-reliable low-latency communications. So a lot of work is going on or has been done in order to address the problems facing this type of communications. The problem, with regards to the problem, the main problem for this type of applications is ultra low latency. So, ultra reliable low latency communication applications require extremely low latency. This is in the range of milliseconds or even sub milliseconds. And problems such as signal propagation delays, network congestion, and processing overheads are just some of the factors affecting ultra reliable low latency communications. Another problem is high reliability. So, ultra reliable low latency communications applications demand ultra high reliability to minimize packet loss and ensure seamless communications. So problems such as channel fading, interference, and signal degradation can affect the reliability of the communication links. So, according to some experts in this field, 5G networks will not be able to meet all the requirements for ultra reliable low latency communication. And this is because, in addition to the guaranteed latency that is contemplated in the 5G specifications, most of these emerging applications will require high time and phase synchronization. They will also require 100% coverage and sub-centimeter geolocation accuracy. So applications such as virtual reality, augmented reality, and 3D video will require terabits per second level transmission data rates, and at the moment 5G can only provide gigabits per second level data rates. So, in terms of the research methodology, we have designed the framework, and within this framework is the problem definition, the literature review, the data collection, the selection of artificial intelligence techniques, the model development, performance evaluation, and analysis and results. So, this study is conducting experiments and simulations to collect data and create data sets that will then be used with machine learning and deep learning algorithms. So the plots below are the results of a simulation to analyze resource allocation, packet loss, delay, and throughput. Uh, The plots we are seeing now are the results of a simulation for packet transmission with priorities in wireless sensor networks. Here we analyze packet size against the packet priority, average queue length, and the wireless sensor network coverage. The plots below are the results of simulation to compare the throughput for scheduling algorithms. The plots we are seeing now are the continuation of the previous slides. So we are comparing throughput between proportional fair, stochastic fair queuing, and round robin. The figures below illustrates the results of a simulation to compare networking parameters. So, okay, the figure below shows the plot of the original dataset used to train a machine learning model for classification using the fine tree algorithm for data analysis and knowledge of feature extraction. The plot below illustrates the results of the machine learning model after training. So we had an accuracy of 100% for validation, which means that the models predictions perfectly match the true values. This is a good indication. It indicates that the model can accurately predict scheduling algorithms or quality of service schemes. The plot below shows the result of a neural network model for regression. As we can see, we had here a very good result as well, which is an indication that the model is performing well and can accurately predict scheduling algorithms. The figure below illustrates two prediction models. The first plot is the predicted result for the delay experienced by users when using the proportional fair algorithm, and the second plot shows the predicted results for the throughput experienced by users with round-robin algorithm. This study is also conducting experiments on network equipment, real hardware, to simulate priority queue, HTTP and CBQ. The data collected through these simulations were used to create data sets and to be used with different machine learning and deep learning algorithms. So the plot below shows the original data set. This is before the training the model. This is the result after training the model. So we had an accuracy for the validation data set of 97.1%, which is a very good result. And this is the test confusion matrix for protocol prediction. We had a result of 100%. This indicates that the model is performing well and can accurately predict protocols on new data. So we are doing experiments with regression models as well. So below is a plot of the original data set for the data collected through the simulations with network equipment. This is the original data set. This is the result after training the model, and as we can see, we had a very good result. We have been. This is the result of the convolution neural network model, and we achieved a very good result, 87.50%, which is an indication that the model has learned meaningful patterns and can make accurate predictions on new data. So we have been experimenting with LSTM networks as well, and here the result is showing that we are not achieving more than 50%, which is an indication that this type of neural network model is not performing well on this task. So, to conclude, based on the experiments and simulations, it's possible to conclude that machine learning and deep learning algorithms can effectively predict traffic and quality of service schemes in communication networks. Research on quality of service improvements are crucial for meeting the strict demands of real-time applications that requires ultra-reliable low-latency communications. And the research on this field improves performance of wireless sensor networks by improving parameters such as latency, reliability, and energy efficiency. So, the efficient resource management through quality of service research optimizes the utilization of limited resources such as bandwidth, memory, and energy in wireless sensor networks. Artificial intelligence techniques such as deep learning techniques are very powerful tools to develop advanced algorithms and models that can analyze and optimize network performance, resource allocation, and quality of service provisioning based on complex data patterns and predictive analytics. Um, So, reinforcement learning and deep reinforcement learning enables autonomous decision making and adaptation by training agents to learn optimal policies and actions in highly dynamic environment. And of course, this leads to improved quality of service provisioning, resource allocation, and network management. With that, with this slide, I conclude my talk, and thank you very much.